Hey class, Mr. Offset here with our 6th lesson in Unit 4, second from last, and it's very closely tied to Lesson 5, our previous lesson, where we looked at conservation of mechanical energy with conservative systems. Now we're looking at non-conservative systems. So if you remember from our last lesson, we said that as long as the forces present were either force of the spring or the elastic or the force of gravity, we could consider those to be conservative forces. But if we had any non-conservative forces, like force of friction, that's a big one. And another big one is our force applied, some external force pushing on our object. Then we need to use this new formula where we have our initial mechanical energy, total mechanical energy at the start, plus whatever the external non-conservative forces are, what the work they do. So again, that would be a force times the distance, or the change in energy resulting from our friction or our applied force. So that's all on this one side of our equation, and it has to equate to the mechanical energy at the end, our final mechanical energy. So just like I stated, our work due to our external forces or our non-conservative forces is equal to the change in energy of those guys, or the force times distance that is parallel to our motion or our displacement. So when we are working with friction, anything that is a resistive force, we need to remember that this work is negative. This is, again, going back to the beginning of the unit where we said that work can be positive or negative. Negative is always going to resist it, right? We're losing energy, so it's a negative joule amount, negative work, right? So the total mechanical energy will decrease whenever we have this resistance, like friction or heat, sound, right? Those are all part of friction. That's where the energy from friction is really going, right? As we're rubbing something together, not a frictionless surface, we're going to generate heat, and we're going to hear some scraping. So we're producing heat and sound. All right, so that is our resistive force, like our force of friction here. Positive work, external non-conservative work force, is from a propulsive or an applied force. That's this guy here. So that's when we're adding energy, when we're pushing something up more. So we're putting extra energy in, therefore our mechanical energy should increase. All right, we have our first example already. That's it for the notes today. I only got 2 examples. So this is a nice quick video, give you guys a little bit more time to work on that homework. So it's giving us a triangle or a ramp, 7 meters hypotenuse, 5 meters elevation gain. We have a 4 kilogram box that's sliding up at 12 meters per second. We want to find the average friction force if its max height is 5 meters. So again, important to understand that max height refers to our final speed being 0. It doesn't directly state it in this equation or in this question, but we do have to be able to interpret this special physics vocab of maximum height, and understanding that whenever we have maximum height, whether it's up an incline, whether it's being thrown up in the air, whether it's a 2-dimensional parabola, we're working with a final velocity at that maximum height of 0 meters per second. Okay, so let's look at this question. They want us to determine the force of friction. So we know we have a non-conservative system. So we're going to be using our initial mechanical energy plus the work done by our non-conservative forces, in this case friction, equaling our final mechanical energy. So at the start, our mechanical energy, if we're saying this is our reference height of 0, we have mgh would cancel out, no potential gravitational energy at the start. We have all kinetic energy, mv squared, plus our work of friction, which is the work done by friction, which is what the question wants us to determine, right? So that'll be the force of friction times the distance that it travels, right? This is the formula that you're given, so we'll keep it consistent. And that's all going to equal our final mechanical energy, which is all gravitational potential energy, because our kinetic energy is 0. So half of mv squared v is 0. So 0 ek. All right. So we got kinetic energy plus friction equaling our final gravitational potential energy, all because we have no speed here and no height here, right? Starting at 0 elevation, ending with 0 speed. Okay, let's throw in our numbers. Let's rearrange it first, actually, to solve for this guy, especially this force. So force of friction is what we're looking for. We know force of friction times our displacement is going to be equal to our gravitational potential energy minus our kinetic energy at the start. And you see that I dropped the cosine because we're working parallel, right? The force of friction will be parallel to our displacement, right? We're going to travel straight up the incline, and the force of friction is always parallel to the surface. All right, let's throw in our numbers. We'll just divide this by displacement. Force of friction is equal to our mass of 4 kilograms, 9.81 meters per second squared, and a height of 5 meters, minus half of mass velocity squared, 12 meters per second squared, divided by that displacement where friction is acting over, right? So the work done by the friction is equal to the force of the friction times the distance it's working over. So we're working with this distance here, 7 meters. So I'm going to divide all of that by 7 meters. And I get force of friction is equal to, and right, we got bigger number, smaller number. And since the force of friction and the displacement are in opposite directions, we're going to use a negative there, right? So this would be negative force of friction because it's in our opposite direction, right? Our reference system with this incline would be positive. Negative force of friction is acting in a negative direction, so we need to incorporate that here, right? Or we would just get a negative answer, and we'd understand that that's just telling us that the force of friction is acting down the slope, right? It's kind of a resistive force. And it'll come up with 13 newtons, right? Negative 13, which is 13 newtons down slope. important to include our direction. All right, that's our first example. Our second example, we're working again with friction, but this time they're giving us the force of friction, or its average force of friction, and we want to determine this second applied force. So we know that we have two external forces now. This big force F here, which is an applied force in the same direction as motion, and we have a force of friction acting over our whole motion. We've got a 45 kilogram block, and at the end it's starting at rest and it's ending at 27 meters per second. So we obviously have some acceleration. We have a change in velocity, and that tells us we have to have accelerated motion. All right, we want to determine force F, and this one's going to be using some of our Unit 3 force analysis because we have unbalanced forces and acceleration. So we're going to be using Newton's second law. Let's start with our conservation statement though. Conservation of energy. We cannot create or destroy energy. We can only change its form. So our mechanical energy at the start plus this non-conservative forces work done on it will equal our mechanical energy at the end. So we have at the start, if we're saying we have a reference height of 0 at the start, we have no potential energy. We're also starting at rest. So this is going to be 0. We have no mechanical energy at the start. But we do have the work of the force applied and this negative work of friction. That will equal our final mechanical energy, which is going to have both kinetic, with this 27 being our VF, and our gravitational potential, which is our 39 meters. All right, they tell us the average work done by friction. We're looking for the force due to this guy. So we have, for both of these, a force over some distance, which is actually going to be the same distance. It's going to be that 110 meters. So this will be our applied force we're looking for. And again, the cosine would be 0. So it's going to not impact this. We're acting parallel to the plane as the question's drawn this force parallel to our incline. So the cosines will cancel out. And we're going to subtract the force of friction, which is given to us. They tell us it's an average of 320 newtons times the same displacement is equal to all of that. I'll actually throw in the numbers here. Half of our 45 kilograms and our final speed of 27 squared plus our mass of 45, gravity, and a height of 39. We're working with much bigger numbers here, so we must have a pretty big force pushing this. So this is what we're looking for. Let's isolate for it. We're going to add the force of friction onto this side, and our distance is 110. So the force is going to be equal to this here, which comes out as 3,000 or 35,200. We are working with much bigger numbers here. sorry, both of those combined, both of those added up will equal 33,619.05 joules. We're then going to have to add in our force of friction, which is 320 times the distance of 110, and we're going to divide it all by 110 meters. Throw that in the old calculator, and we get our applied force coming out at 626 newtons. And that would be up slope. All right, that's it. Nice and short lesson. Only thing that changed is this idea of our non-conservative force, which is most often just going to be friction. It could also be some externally applied force, like a hand pushing this thing up the incline, or like some thrusters on a rocket, or engine revving in a car, right? All examples of external forces that are going to change our conservation of energy by adding in this non-conservative force, which we're going to add to our initial mechanical energy, so that our final mechanical energy is a product of that external force and our initial system. All right. Thanks for listening, guys. Let me know if you have any questions.